Yes. Today I'm gonna present an engineering problem, modeling and analyze using the point process theory. The title is How much can RIS augment sky visibility, which is available at archive. Uh, and this work is jointly worked with Professor Frank Pacelli. I will try this. I want to introduce shortly myself. Is it okay? Yes, again, my name is Junse Lee, currently affiliated in Sungshin University, joined in 2021. I did PhD on the Dr. Bacelli at University of Texas at Austin. My topic was modeling and analyzing wireless network using stochastic geometry. Uh, I tried to investigate the impact of the correlated shadowing thing and try to analyze the advantages of the MIMO on the class 1 bipolar networks. I have some working experiences about 6 years in Samsung Electronics before PhD and after PhD. Before PhD, I was involved in the LTE base station project. I mainly focused on the modern features, Samsung Smart Scheduler. Now it is known as the CMN, and also did some RF related things. After PhD, I joined to 5G Exynos modem team. I mainly focused on the design of the digital front end, which is the compensating analog characteristic in the digital domain. These days, I'm focusing on the analysis of the LTE satellite networks. So here is the structure of the talk. So I will introduce the motivation and the objective of this research topic, and then we'll show you the system model for the outdoor network. And then I will define what is the visibility angle and try to show you the distribution of visibility angle without and with RIS. I will show you some numerical results and then we'll conclude this presentation. So here are the motivations. Actually, I'm doing some research projects with the Korean government and the research institute related to the national defense. They always ask that how many satellites are connected to a user, to a ground user, which is related to the service continuity and the multi-connectivity. They also ask how many satellites are needed for a certain outdoor environment because they want to reduce the cost for under the certain level of performance. So these two questions are the main motivations of this research, and the keywords are here. So I really want to consider the outdoor environment, the LOS visibility, which is the important physical property of the millimeter wave bands. I tried to consider the connectivity of terrestrial users to NTN network nodes and the visibility and coverage analysis extended by some other network nodes. Here I used the RIS. So yes, I bring the main objective here. First of all, we try to propose a novel framework to analyze the ground user's sky visibility using the point process theory. And then we try to use RIS to increase the visible region by the ground user. This is the high-level picture. So the user is at the ground. The vertical lines, you might think that these are the buildings. And I installed RIS here. So without RIS, the LOS visibility at this altitude only available from here to here, right? But with RIS, this can be extended. So this is the high level figure for this project. So let us move to the system model. First, initial stage of this project, we try to consider to solve the 3D model. This is the top view of the 3D model, and you might think that the line segments are the buildings. But it is somewhat complicated, definitely at the initial stage of this project. So we focused on the user's view direction, which is illustrated as the dot arrow from the user. And this is mapped to the right figure. We try to simplify the model in the two-dimensional scene. So the user is here, and the vertical lines, again, you might think that these are the obstacles or buildings or blockages. And XI and HI are the locations and heights of each building. So when you see here, you can see that the third building, which is located at X3, blocks the sky visibility most. So we define theta as in this way, the line, the line connecting the user and the top of this blocking building, and the ground. So theta, we will say this is the blockage angle, and naturally psi, which is the pi over 2 minus theta, we will define this as the visibility angle. So basically, we try to give some distribution under the model xi and hi of the theta and psi. One more thing is that we will use the location x plus and h plus as the location and height of the blocking building, which creates the maximum blockage angle as depicted in this figure. So we proposed many the outdoor network models. First of all, we say this is model if xi follows a homogeneous Boston point process with intensity lambda. And hi, if hi is IID exponentially random variables with parameter mu, we say this model is this outdoor model is the model, same as in the queuing theory. We also consider the variant models of model. We say MD model if HI is a fixed value as 1 over mu, and DM model if the distance between adjacent buildings are fixed as 1 over lambda. We can definitely possible to extend these models like the wave distributed height or some other models from queuing or some other theory. But in this presentation, we mainly focus on the model. Definitely the thing related to MD and DM, you can check that in the paper posted on the archive. So the first thing is we try to give the distribution of theta, which is the blockage angle. So as you can see here in the model, the CDF of tangent theta can be derived as the exponential of minus rho over t, where rho is the lambda over mu, the multiplication of the density of buildings and the mean height. By changing of random variables, it is possible to obtain the distribution, the CDF of theta gain. The main philosophy to obtain this one is that by using the Laplace functional of PPP, you may find the detail in the archive post. Also, we in the paper we obtained the same result under the MD NDM model.
Is it still Fresher?
I'm sorry?
Which kind of distribution is it for EM, MD, and ND?
Oh, yeah. So MD.
No. The result, the distribution of the handle. Is it still
It's
Fresher?
somewhat different. Somewhat different with somewhat different with MM model, but
okay.
Yes, I skipped these two things. I want to focus on the MM model.
Okay. But I was gone by Moon or something like this.
The French thing is interesting and surprising, right? So, and it comes that in the Poisson or whatever in the steady state, there may be a wall close to you.
Yeah.
And that's the reason for the depression. So it's out of this type. But everything.
Yes, actually, some modeling research sometimes asked by many engineers how much your model is close to the real environment. Well, this kind of the question is typically hard to defend because it is needed the real data from the real network. Fortunately for this case, I found this data in the 3GPP technical report, which is that the ROS probability with respect to the elevation angle on the three scenarios, dense urban, and suburban and rural scenarios. With this data, and under our MM model, we compare the data and we can see that it is quite well matched by tuning low, which is the lambda over mu, which is the product of the intensity and the mean height. So in this way, we can see that our model is quite nice and quite close to the real environment. And the next thing is that we want to investigate the distribution related to the blocking building, which creates the blockage angle. So here, X plus and H plus are the main interested things. So the theorem here is that we obtain the joint density of X plus and H plus using the closed as the form of the closed form. By marginalizing them, we can definitely obtain the density of H and density of X also. We will use this distribution thing for the next section, which will be considered the distribution of the obstacle angle using the visibility angle using the RIS. I believe most of you already know what is RIS, but I want to talk about it shortly. So basically, RIS is the meta surface which changes the channel environment in order to enhance the signal quality. It is known that the RIS has three modes: transmissive, reflective, and hybrid. Transmissive mode is that the signal passes the RIS, this meta surface, and the reflective mode is just the reflection. And hybrid mode use the both transmissive mode and reflective mode concurrently. We focused on the visibility extensions by using the RIS, especially if RIS are installed on the top of each building. I will show you it later. So here is the system model again. As I said, the RISs are installed on the top of each building. So the story here is that the ground user tried to transmit his signal to the RIS installed on the top of the blocking building, which creates the maximum blockage angle. That would be the goose trade good strategy to enhance the visibility. So what I will do is theta is the blockage angle, and theta t xh, the superscript t implies the transmissive mode, and the underscripts are the location and height of the blocking building. We will try to compare theta and theta t by deriving the distribution of theta t. Reflective mode can be obtained similarly with the transmissive mode, but here we will focus on the transmissive mode in this presentation. So yes, so here is another theorem. So we want to obtain the CDF, the distribution of the theta t, the blockage angle at the transmissive RIS. So the transmissive mode of the CDF of theta xh is definitely function of the network parameters. The low is lambda over mu again, and something like this. So this figure illustrates the comparison of the distribution of theta and theta xh, which are the blockage angle without and with RIS. This line is the CDF of the blockage angle without RIS, and these three lines are the blockage angle with RIS. From the stochastic dominance, we can see that without RIS, the blockage angle will be larger from what we can see from this figure. So I think I'm somewhat fast. Yeah. So I will move to the numerical part. First, I want to compare the visibility things without and with RIS in the angular domain. So I will define gamma 1t, gamma 2t as in this way. Let me show you again. So psi is the visible angle without RIS, and psi t is the visible angle at the RIS installed on the top of the blocking building. Definitely psi t should be larger because that is the due to the geometry thing. So by definition, gamma 1t and gamma 2t, it starts from 1, and it will increase as rho increases. Rho is again, which is the product of the density of buildings and the height of the building. So the larger rho implies the city is more crowded. What you can see is that if the city is more crowded, if the building height is more high and the density is more dense, then we can expect more gain from the RIS in terms of the visibility. We also try to see the gain of the RIS in the linear domain. So here, H and X are the height and the location of the blocking building, and the capital H, we say that is the height. Oh yes, I should say this one first. I will deploy NTN nodes at the same altitude, as in the circles. Circles are kind of the NTN nodes. I will deploy these nodes at the same altitude, and H and X again. These are the height and location of the blocking building, and the capital H is the height over the height of the blocking building. So without RIS, small LXHH would be the visible region without RIS. And the capital L, XH, H would be the visible region with the aid of the RIS installed at this building. So we will compare these two things. Again, we considered under the MM model and the transmissive model, and it is possible to obtain the length of these two things in this way. Since we know the distribution of the joint distribution of the blocking building, the height and location of blocking building, by deconditioning it, we can get the expectation of the length of the visible region without and with RIS. And if we deconditioning it one more time using the X and H, then we can see that without RIS, we can expect the finite length of the visible region, but with RIS, we can see the infinite length of the visible region by using some distributions we obtained in the theorems. We also define the probability of coverage. Here, we assume that N10 nodes are distributed as the homogeneous PPP with intensity mu at altitude h plus h. So you might think that the N10 nodes are deployed under the top of the line as the distributed as the homogeneous PPP. And we define tau h, xh as the conditional probability of the coverage given that the height and location of building is here, and we also condition that there is no initial visible NTN nodes. This equation would be more intuitive. We try to compute the conditional probability where the condition is that there is no satellite at the first stage without RIS, but we can observe, but we can calculate, we want to calculate the probability that there exists at least one visible node with the aid of the RIS. It is possible to obtain in the closed form, and by unconditioning using the distribution of the statistics of the blocking building, we can obtain in this way as the closed form. And the next slide, this figure shows the illustration of this equation. And we can see that tau h is the increasing function with respect to h nu, the altitude, and the density of the NTN nodes. It is very intuitive because if h, the height become larger, and if the nu becomes larger, there will be more NTN nodes, and it will lead to the increased value of the tau h. We also provided some numerical things more by setting the lambda and mu and some other network parameters. We follow the cases as described in the 3GPP, and under some lambda and mu, we can see the gain by using the RIS in terms of the blockage angle or visibility. And we considered two scenarios. The first one is HAPS, and the second one is satellite. By setting the capital H and nu as in this way. So this is the case study. So here is the conclusion. I think this research well describes the visibility thing based on the function of the network parameters, and we also observed the gain of RIS in terms of the visibility. So possible future research direction could be this. We consider the simplified 2D model, but we can extend it to the 3D model. And if we consider the connectivity, not the visibility, then we might think about the multi-app scenario and extending it in that way. We may think about some refined statistics, and here we only consider the visibility, but we might think the coverage analysis, the coverage probability thing on the this network model. So that's it. Thank you for your attention, and please ask me if you have any questions.
So with respect to the multi topic, the highest building, so you can access all the building.
I'm sorry, could you repeat again?
With respect to the multi-hop future research direction.
I cannot hear you.
If you do multi-hop, look. Yeah, so if you do multi-hop
yes.
possibility, eventually you are going to reach the highest building.
Yes.
So that means you can access the entire sky, right?
Yes, I think so.
At infinity. Highest building, if you have exponential, there is always a higher building. So in a sense, it's degenerate.
Okay, okay.
It's a translation line.
Thanks.
I have a brief question. So I have a little different question. So you have a hat, right? So
Yes.
the hat generally is a vertical polarization of signal,
Yes.
and from ground you have the linear polarized signal. So is the RIS able to preserve the polarization aspect of the signal?
Actually, in this topic, we only consider the visibility.
No, not in this topic. I mean, general question I have regarding polarization of signal. Thank you.
Well, I haven't thought about that a lot, so I will try to find the answer and we'll share it to you.
I have a question. So in your model, the waves are always propagated like a line, right?
Yes.
So is there a possibility to consider the beam width, that is might be inversely proportional to the band, like the RIS reflex signal, that is like a beam width like 1 or 2 degrees?
Basically, that is yes, definitely here we only consider the beam propagates like a line, and I assume the RIS visibility here or under the millimeter wave story. Well, I'm not sure I understand you. I do not understand your question well, but the beam is. I'm sorry, I think I do not catch your question well.
I mean, multipass or
No, I mean if there is a beam that you have the visibility and the beam has some beam width, it can illuminate a small area, not a point. Yes, you model your user as a line rather than a point. The illuminated area. So probably this is some nonsense question.
Kind of the opposite question where you wondering if you can illuminate like a small segment instead of the original.
Yes.
yeah. So if you have line of sight, I mean, even if you have a beam with a beam width. I mean, if the thing is inside, that's what happens in classical massive MIMO. You know, there is a beam width, but if you are within, you have an increase of the signal power at this point. And for visibility, I mean, so there may be question about energy, right? But for the visibility question, I mean, being with the beam is a sufficient condition for visibility.
Okay, I may make my question a bit more visualized. So imagine there is a building, there is another building that is higher, that you have a line that can connect these two buildings. And then when it passes the blocking building, then as a wave you will have a diffraction angle, a small beam that illuminates area, not a line, but it's like this. So it's I mean, the wave effect perspective. So if something is blocked, but blocked, it's very close to the line of sight. You have.
Actually, we do not consider the case. I understand now what you mean, but basically, yes, that effect is not considered. I just consider the visibility as the line to make some for simplifying. But yes, definitely that is the possible physical phenomena, but here that is not considered.
Okay, thanks.
The important thing to keep in mind also is that the RIS should be a very elaborate thing, because it has to follow the satellite to establish the transmissive or the reflective, right? So we go from the user to the RIS, and the RIS does the adaptation. So, but it's not a passive RIS, must be intelligent enough to be informed to the satellite and follow it. Right? So this would be expensive devices to be transmissive or reflexive because of the motion of the UAV or something. Any other question or comment? Okay, then thanks, Junse.